Hello everyone, my name is Dmitry Chmadanov, and today I'm going to talk about incident supporting Visual Cloud Computing utilizing Virtual Network Embedding project. The purpose of this video is to show benefits of novel Visual Cloud Computing paradigm utilizing Virtual Network Embedding versus traditional cloud computing over regular best effort IP network in disaster scenario. We discussed the difference between best effort IP networks and software-defined networks in our previous demo video. So you're welcome to see it again following by the link below. So what's the difference between cloud computing and visual cloud computing in disaster scenario? To answer on these questions, let's first discuss what the main problems in disaster we can face with. First of all, in disaster we have two crucial components. It's available hardware resources and the time. And former can of course save later, meaning that using more hardware resources allows you to provide better response and therefore save time and as a result save more lives. However, current state-of-the-art technologies for visual computation such as video streaming or cloud offloading cannot scale with multiple sites because they're tied to particular hardware, because they're coupled with particular software running on this hardware. So the idea of visual cloud computing instead, first of all, scale by different sites when we decouple our software implementation from the hardware itself with using virtualization technologies, and further allowing moving our computation closer to the network edge into the FOX. In order to enable visual cloud computing, we first need to see on the collection, computation, and consumption ecosystem in the disaster incident case. Usually, what we have in disaster is that collection side is located remotely from our computation resources and from the consumption side. So all these located at different sites, and they're separated usually geographically. However, if we want really to scale on such topology, we need use resources as in collection side, as in computation, as well as in consumption side. Moreover, idea of having this visual cloud computing is that in our collection side, we can do some small instance processing, for example, reducing the frame size or do some contrast enhancement for the images, so that we can speed up the processing in our computation side. Moreover, we can offload some computation in the consumption side to do some local processing in terms of, for example, pan and zoom with caching locally, so that the whole system will benefit from this performance. However, there is a reasonable question: how can we apply our visual application into visual cloud computing paradigm? To this end, we intend to use Virtual Network Embedding paradigm, which allows us to map virtual network on top of physical network. So physical network is our resources, is our 3C ecosystem we have. So virtual network instead is something which can be transferred from our application demands, so that if our application consists of steps like preprocessing, tracking, and HCI analysis for object tracking, we can split them to 3 different nodes. At the same time, we can decide how many resources we need for doing particular operations. So that one can notice that all these virtual network represents kind of virtual paths from our raw data through some intermediate steps to our final output where we track this object. Further, based on these virtual network requests, we can use virtual network embedding algorithms to basically match these virtual network demands represented as virtual network on top of physical actual network. To this aim, we designed special virtual network embedding algorithm which can address challenges of doing such virtual network embedding in disaster incident scenario. This algorithm is called Nexus, and we establish its particularity through extensive simulations, where one can observe how Nexus benefits in presence of node failures, like low and medium node failures. However, in this particular demo, we don't need to show the benefits of Nexus itself. We need to show benefits of visual cloud computing in general, in contrast to cloud computing. So, we are not going to do some tricky and difficult test bed for showing benefits of Nexus itself. Instead, we came up with simple test bed similar to previous video, where in one case we're doing cloud computing over traditional IP network, which results in congestion in the network in the middle of this test bed. Moreover, in the cloud computing case, we do our tracking and pre-processing on the same site, particularly in host 1. And as you can see, the host 1 has the biggest resources in the whole topology, like 4 cores, 4 GB of memory, and 30 GB of hard drive, in contrast to our folks allocating on host 2 and host 3. So host 2 in our testbed scenario acts as a collection site, so it has local access to the data. And host 3 acts as kind of consumption site. For simplicity, we assume that we just need to store this raw data on this remote machine. So, in visual cloud computing, utilizing virtual network embedding, we are using SDN optimization of the network in the middle to tune this network for particular tracking application, so that we mitigate our congestion. Moreover, in this case, we run our pre-processing locally on the host 2 because it has access to the local data, to our raw data, and it allows us to send already processed data directly to the host 1 and save this pre-processing time on computation on the host 1. So as we will show later, it allows us to run tracking online in contrast to cloud computing over traditional IP networks, which where in this case we have to wait some additional penalty time before we can track the object itself. So as a result, we're using the same resources as in previous cloud computing case, But applying Visual Cloud Computing allows us to do online tracking, whereas cloud computing has time penalty and it can be applied only for non-real-time context for the same data on the same topology. Before we will continue with actual experiment, I'd like to say a few words about testbed setup. For reusability of previous testbed, we took a snapshot of our host 1 from the previous video, so that we don't need to install Loft again. And we reused previous topology, substituting different parameters to the R specs for links and nodes. In the cloud computing scenario, our workflow as follows. First of all, we start sending our raw images to the remote storage. At the same time, we start sending our raw images to our cloud, which is host 1, for computation. Before we can track actual image, we first need to pre-process it in the cloud, as we don't have all these images locally. These, besides congestion, cause additional time penalty for tracker to start tracking the object and results in additional waiting time for our application. As in previous video, we used POX controller to emulate work of regular network. So we can launch it. Other for window is used for transferring our images to the host 3 for storage. Another window is used for doing local processing, which is contrast enhancement before tracking and then the actual tracking. So we can start our transferring, then at the same time we can start doing our local processing and sending data to the host 1, and then we can launch our application itself to track these images. So we need to wait until this app will be initialized. And now we can see result of the tracking. So we're almost done. Now we can see that our storage transferring time takes in total 300 seconds in this scenario. Not 300, but 280 seconds in this scenario, meaning that approximately we need half second to transfer one image. But the main result is here. Please pay attention for the total waiting time of the application. It's not equal to 0, but it's equal to 317 seconds. Now let's do actual experiment with Visual Cloud Computing scenario. To do so, we're gonna again transfer our raw images from host 2 to host 3, but now we will also launch our local processing at this host 2, meaning we are doing this pre-processing and the fork. At the same time, we can concurrently send our data to the host 1, assuming then we can pre-process image faster than send it. In this case, we can run both pre-processing and sending our data concurrently, so that there will be no extra penalty for the tracker on the host 1. Moreover, as we are using Virtual Network Embedding, in this case we will avoid this congestion and provide guaranteed 40 megabits per second from host 2 to host 1, because as we will see from as we saw it earlier, actually, the 40 Mbps is require a tray to run loft real time, so we don't need to provide more like 50. In this case it can be treated as over provisioning. So we'll start our local processing on host 2 and start sending our data and send them to tracker on host 1, and host 1 will track. So our expectation from this experiment is to see zero waiting time on host 1, meaning that we can track in real time. Again, we are launching our SDN controller. And then we can log in to our UI. Which now has additional virtual network submission form where one can easily add nodes, play with them, build whatever virtual network wants to submit. In addition, it's possible to specify additional resources or delete some resources. Let's say we'll delete all these additional nodes. However, for simplicity of this experiment and to avoid dealing with node virtualization technologies, we are not going to use a full virtual network embedding paradigm. As in previous case, we have initial detected only our switches. So to discover our host, we need again to ping from each of the hosts. So after we did all ping from all hosts, we can observe our actual network topology. So referring to our topology, now we can see that this is our host 2, which has local data. This is our host 3, which is assumed to be our storage, and this is our host 1, which is assumed to be our computation side in the cloud. So to emulate work of our virtual network embedding algorithm, we can easily allocate just 2 virtual links between host 2 and host 1, where we assume 40 megabits per second is enough transfer rate for our main traffic, and between host 2 to host 3, which is our storage, we assume 50 megabits is enough. And now it's allocated. Also, we can ensure that we allocated resources appropriately. So now we can see that our link between host 2 and switch 2 has only 10 megabyte available capacity. At the same time, link between switch 1 and switch 2 has also 10 megabyte available capacity, meaning that 40 Mbps pass from host 2 to host 1, going through the shortest paths and the link S1, S2. At the same time, we can see that to avoid congestion here, now our concurrent traffic will go through switch 1, switch 3 and switch 2 path, like this. Now we are ready to do our final experiment with Visual Cloud Computing. So now, instead of doing local processing on the host 1, we can do this locally. To this end, I'm going to log in on host 2. Here I will run local processing script. So as usual, we are going to transfer our data to the host 3 and our main traffic to the host 1. So I'm going to start experiment with sending concurrent traffic, then I can launch our local processing and send our data to the tracking application and then launch the tracking application itself. So now we can see how we are tracking. So now we can see that it takes on 100 seconds less or transferring whole 500 images to data storage. At the same time, we can observe zero waiting time for tracking, meaning that we can track in real time in contrast to cloud computing scenario. We did 10 trials of each type of scenario and outline our final result in this table. Now we can see the storage transfer time for each frame. It takes almost 600 milliseconds. In cloud offloading case where we have congestion, and avoiding congestion allows us transfer faster. Moreover, we can see how preprocessing time in VCC case actually is higher, but still, because we are now able to run concurrently our preprocessing and transferring, we can see that waiting time now is zero, meaning that we can track in real time, in contrast to previous cloud offloading scenario where our tracking time, where we have penalty almost 1 second for each frame before tracking. Tracking time slightly differs in VCC case, but still the same. So, and as a result, estimated throughput is low, first of all due to congestion, and secondly, throughput is lower because we have to wait for pre-processing in the cloud offloading case before we are doing tracking. In this case, we can utilize the whole 40 Mbps pipe. And also the final time, in VCC case, our final time is equal to tracking time per frame. In the cloud offloading case, this final time is equal to tracking plus waiting time, and much higher than in VCC case. So based on these results, we can conclude that VCC is more flexible and scalable paradigm and allows us to do visual computing in disaster scenario much faster, saving not only time but also human lives.